Today we're going to talk about uniform circular motion. Uniform circular motion means an object moving in a circle with constant speed but not constant velocity. The velocity is not constant, of course, because the direction changes. For example, let's say we take a rope and we tie it around a rock and we twirl the rope around at a constant speed. This would be uniform circular motion. To make something go in uniform circular motion, we need what's called a radial force. That would be a force pointing from the object straight in toward the center of the circle. There are many types of radial force. There's no such thing as a radial force by itself. It has to be some other real force that we've talked about, a number of those before. One of the most common ones, of course, would be the tension caused by a rope. Another one could be static friction force caused by the road, causing a car to be able to turn. Also, we could have a gravitational force caused by the sun, which would make a planet be able to orbit the sun. Even the normal force can be a radial force. It's a little hard to maybe understand how that would be, but we'll see that in a while. In class, we derived the equation for uniform circular motion, abbreviated UCM because it takes so long to write. And that equation was that the radial acceleration is equal to the speed of the object divided by the radius. The radial acceleration is actually a vector here. We're looking, though, at just its magnitude rather than any changes in direction. You don't have to know how to derive this equation, but you certainly should be able to use it in calculations and Newton's second law for uniform circular motion. So you might have thought that was going to go away. You never have to see it again, but it's still there, and we're going to do some problems on it right now. First, let's do a numerical answer so you get an idea of what this is like. Let's say we have a circular track that has a radius of 100 meters, and let's say we have a car going in this direction, and this would represent the velocity of the car, and the force that's going to cause this thing to be able to turn would be the static friction from the road, of course. And you certainly don't have a rope attached to the car, or there's no gravitational field pulling it. So the static friction of the road is what enables the car to go in a circle. Remember, it's not kinetic friction. Even though the car is moving, the interface between the tire and the road is not a sliding situation. The tire is rolling, it's not sliding. If it were sliding, it would be kinetic friction. And also, if it were sliding, the car probably would not be able to go in a circle. So let's put down a static friction of 0.9, which is typical for a car on a road. That's pretty high compared with some of the numbers we've seen for example, a wood block sliding across the table, but certainly car tires are designed to get good traction, and roads are designed to be a little bit rough, so you get good static friction. The other thing we're going to take a look at here is how fast can that car go around that circle. So let's say you were designing a road that had a radius of the turn of 100 meters. How fast could cars go around that turn? We're going to use a flat road here. Generally, turns are banked, but just to keep it simple, we'll use a flat road. Okay, let's get started with this problem. First thing we want to do is realize that this up in the air view, bird's eye view of this, is not a good representation. We need to look at the car either coming at us or going away from us. It'll be a little safer seeing it go away, so we'll do that. This would represent the car. Of course, we always start with a dot. The next thing we do is put down our mg. And since it's just a car on a surface, this would represent the normal force. And of course, those would be equal. We've seen these problems many times, so we don't have to calculate that Fn equals mg. We just kind of understand that. Now, if the car is going to be turning to the left, the force that allows it to turn is provided by the static friction force. So this free body diagram then would give us both the x and y version of what's going on with the car. Okay, so let's just make a note to ourselves that Fn equals mg. Now, the complicated part of this, that was pretty simple. The complicated part of this is to write Newton's second law for uniform circular motion. So that's going to be F equals m, in this case, a radial. And we're going to expand that m radial into mv squared over r. And as we said before, the force that causes this, the radial force, that radial force is the static force of friction. That, of course, could be replaced by mu static Fn. Bring down the mv squared over r. And the Fn, as we just saw a few minutes ago, can be replaced by mg. So even though this is circular motion, Newton's laws work on it as well, as long as you put, instead of regular old a in a straight line usually, we put in v squared over r, which is the radial acceleration. Okay, now we can see here that the m's are going to cancel, so let's wipe them out. And let's solve it for v squared. You might say, well, why not solve it for v? We'll just keep the radical out of there to keep it simple. So we'll just write v squared equals mu static gr. If we need to take the square root, of course, we can do that. Now let's go back and see what we had for our car. I'm going to bring the equation back up here so we can have it close by. We said it was v squared equals mu static gr. Now we have values for those things. We know that mu static, oops, I made a mistake up here. This is not F static, of course, this is mu static. For a force, it would have to have units. This does not. It's the coefficient of friction. So we have to repair that mistake. Okay, so here we're going to put down then the value mu static, the coefficient of friction between the tire and the road. We're going to put down 9.8 meters per second squared. And finally, the radius of our circle, 100 meters. Now, to get your calculator out, punch this in. I'll do it. You do it. Everybody should have his calculator out, just like everybody should be taking notes on this. So I'm going to punch mine in silently. Do the same yourself. So if you did this correctly, you should end up with something like 29.7 meters per second. So that would be what? That would be the maximum speed that this car could go around in this uniform circle of radius 100 meters and coefficient 0.9. That's the maximum speed the car could go before it started to slide. So having done this problem, if you're not sure of what we did, you can replay this part of the video. If you have questions, send me an email or talk to somebody in class. It's not a difficult problem, it's just different than what we've done before. Let's do another problem. In this problem, we're going to take a look at, let's say, a roller coaster going through dip. Now, usually in our free body diagrams, we don't draw roads and things in here, but if we don't do that, we're not going to be able to tell what's going on here. So this dot is going to represent either a car or a roller coaster car going through a dip. Now, if you've driven a lot in the country where there's a lot of up and down roads, you're familiar with this, or if you've been on roller coasters, you know that when the car goes into the dip at the bottom of the hill, how do you feel? Of course, when you do that, you feel heavier. So, feel heavier. Now, what is heavy in terms of physics forces? The weight you feel you have is the normal force. Your actual weight is mg. So in this course, since you feel heavier, if we draw in mg down your weight, the normal force would have to be larger than mg, and that would be the normal force pushing up on you by the seat in the car. Now, because these two are equal, you can see that the sum of those two forces would point up. Let me move this down a little bit so we can see the circle. That's not going to work. Let me try from over here. There we go. Okay, so let's pull this thing down a bit and see what we've got. Let's continue the circle. I know the road is not going to do that, but let's just pretend it did. So this, I lost my normal force. The sum of these two forces would point toward the middle of the circle. I kind of missed on the shape of the circle. Let's fix that up. Okay, so the sum of those forces points toward the middle of the circle. So if we drew this as a free body diagram, it would look like this, and we can box it. But which direction would the acceleration go? Since the force points toward the center of the circle, whatever direction the sum of the forces points, that's the same direction the acceleration points. So the radial acceleration would point directly up toward the center of the circle. Of course, we don't put AR inside the box because it's not a force. Okay, let's do Newton's second law and see what happens. So net force equals MA, not just regular MA radial. And let's put down the sum of the forces, calling the direction toward the center of the circle, agreeing with the acceleration. We would call that Fn, and mg being in the opposite direction would be minus mg equals mv squared over r. Now, this is a little more complicated than the last one. The question might be, what are we going to solve for? Let's solve for two things. Let's find the guy's weight, and let's find the normal force pushing up on the guy by the car. Okay, this is not too difficult to do. mg can be calculated on its own. So let's just jump down here and say that mg would be equal to, let's say the guy is 70 kilograms. That would be roughly 155 pounds. And g would be 9.8 meters per second squared. Let's run a calculation on that. And what we find is that the guy weighs 686 newtons. Remember, we said a newton is approximately a quarter pound. So this would put him somewhere maybe 150 pounds. Okay, I already said that as an estimate up here because a kilogram, 2.2 pounds of something has a mass of 1 kilogram. Okay, so we found the guy's weight, 684. Let's now solve for the normal force. We'll go back up to this equation here, and it's pretty easy to see that the normal is going to be equal to mv squared over r plus mg. We could factor out the m and do it that way, but I'm going to leave it like this, since a lot of times when people do that, they forget to use the m to install a number for it, let's say. So let's put some numbers in. We have 70 kilograms, and let's say that the roller coaster is going 20 meters per second squared, and let's say the radius of that turn is about 15 meters, and I'm going to have to move this over a bit, and let's add the mg on. Normally we would say plus mg and substitute the values, but because you already calculated it down here, let's just pop that number into the problem. So when we do this calculation, get your calculator and see what you get. Okay, so I got a value of a normal force of 250, 20 or 2550 newtons, so 2,550 newtons. Now looking at the guy's weight, we see that that's very roughly about a little less than 4 times the guy's weight. So this guy is going to feel like he's being squashed down into the seat in the car because he's going to feel like he weighs almost 4 times usual. This would be an additional 3 Gs, as it's called. In other words, he would feel 3 times additional heavier compared to his original weight. So if we did it in pounds, he's about 150 pounds. In this situation, he would feel like he weighed about 600 pounds. That would only be for a short period of time, so it wouldn't cause any damage to him. That's fairly small G-force. So here's our normal force. Okay, so that's that. If you have any questions on this, again, you can look at the video over, or you can talk to somebody, or you can send me an email. If you understand this, put a little check mark there. If you don't understand it, put a question mark there. Okay, now let's take a look at the guy when he goes over a hill on a roller coaster, or over a little rise in the road in a car. We're going to have to change some of those numbers a little bit. We're still going to keep the ones we had before. We're going to have his mass equal to 70 kilograms. And we might as well put his weight down there because we might need to use that also. So this would be his weight. We'll keep the radius of the circle at 15 meters, but when you go in a roller coaster, when you reach the bottom, you're going pretty fast down here. As you go up to the top of the hill, you go slower. So we're going to take that real life example and change our numbers a bit so we don't get some really crazy answers that would be unrealistic. So let's make his speed at the top now only 5 meters per second. Okay, so what are we going to do? We're going to do the same thing we just did. We're going to draw part of our circle. We're going to put the guy right here, and we're going to put his weight pointing down. And you probably know from going over a hill rapidly, how do you feel? First, you would feel a little bit lighter. Could you feel so light that you felt weightless? Yes, we'll take a look at that after we do this problem. Okay, so now we have to take a look at the normal. And the normal, because the guy feels lighter, this has to be smaller. Depending on how fast he's going, that could be just a little bit smaller than his weight, or it could be a lot smaller, or it could be 0, meaning he feels weightless. Okay, so let's do our second law calculation. Sum of the forces radial equals ma radial. And since the center of the circle is below the guy now, let's box our free body diagram, the acceleration would point down toward the center of the circle because that, of course, is below the guy. Right, so that direction is going to be called positive. So we would start writing, adding our forces together. The positive force Fn plus the negative, wait a minute, I messed up there. It's not Fn pointing down. That's mg. Okay, so let's try that again. So pointing down would be mg as a positive force. Adding on the normal force, which is opposing the direction of the acceleration, that negative force being added on would make it look like mg minus Fn. And then that's going to be mv squared over r. These kind of problems get finished very quickly. There's only 1 or 2 lines in them generally. So what are we going to solve for now? We already solved for his weight before, so that would be kind of silly to do it again and get the same answer. So let's solve for the normal force, and that would be mg minus mv squared over r, whereas on the last page we had mv squared plus mg. Here the mv squared over r is going to be a negative value. Okay, so we'll put the mg in as the 686 that we already know, and subtract from that the 70 kilograms. Now we're only going 5 meters per second, and that gets squared, and we'll keep the same radius of turn on the hill, the radius of the circle on the hill, and we'll come up with that. So put your calculators out. Let's see what we get here. Okay, I don't know if that's right. Okay, yeah, the answer I got is correct. I double checked it, and what we find out here is that his normal force, or the weight he feels he is down to 569 newtons. So what does that mean? He feels a little lighter. So just kind of a little bit of floating feeling maybe, because he feels lighter. Let's change this number here and make it a little more interesting. Let's change that 5 to 10 and do a calculation. So now he's going to go over that hill at twice the speed. Let's see what we get there. Okay, now his normal force is down to 219 newtons, and that means that he weighs maybe about 1/5 as much as he did when he's on level ground. Not 1/5, 1/3 as much as he would on level ground approximately. So 3 times that would give us very roughly in the 686 neighborhood. We could keep doing this until we made the guy's weight disappear, but we don't have to do that. We're going to do a separate equation on that, and we're going to find out what speed does he have to go over that turn for his apparent weight to go to 0. His real weight will not go to 0, but his apparent weight will go to 0. So let's try that. Okay, we'll take the same given we had before, but now we're going to solve for the velocity instead of the normal force. There's a real good reason for that, which we'll see in a minute. So he's going to go over a hill, and when his vehicle is right here, it's going to have a velocity to the right, and the first thing we would draw in here, of course, would be the guy's weight, mg. Now, this is something that I don't think we've talked about too much. To feel weightless, what has to be the situation? To feel weightless, you have to have your normal force equal to 0 newtons. How could you do that? Well, you could go over to the window, open the window up, and jump out of the window, and there would be nothing supporting you. You would feel weightless. Or you could go on a roller coaster, or go down a steep hill, you would feel weightless. When people who aren't used to being dropped, essentially, when they're dropped, they feel like their stomach is kind of coming up against their lungs. And that's actually kind of what happens. We'll talk about that some other time. But it makes it a little difficult to breathe if you're totally weightless initially, because it's not something you're used to. If you relax, that feeling goes away. But very few people relax when they're going straight down from 400 feet in the air on a roller coaster. So we're just going to take the guy over a little hill, but at a fairly good speed so we can make him feel weightless. So let's write Newton's second law, as we always do with Newton's second law problems. The sum of the forces on the guy in the radial direction would be equal to NA radial. And we usually would say here that the radial acceleration, the radial acceleration would be pointing down toward the center of the circle, and that's the case here. But the thing that's different up here is that since the normal force is equal to 0, the only force acting on the guy is mg. In other words, he's essentially in free fall. If the car weren't there and he were just sitting in the air, he would be falling or have the feel of falling. So let's substitute in, and down here the sum of the forces is just mg, and ma radial is mv squared over r. Not too much complication here. Cancel out those two m's. What we find out is that the speed that he would have would be v squared equals gr. Or if you want to solve for v alone, it would be the square root of gr. Not too much going on here, so let's put the numbers in and see what we have. That would be 9.8 meters per second squared. And the radius of our circle is 15 meters. So how fast does he have to go over that thing to feel weightless? So we're going to take the square root of 9.8 times 15. So he would have to go over that at about 12.1 meters per second. That's roughly, very roughly, 25 miles per hour. Okay, so that's how you can figure out how fast somebody needs to go to be weightless. You might be thinking, what would happen if he went faster than that? Good question. I think we can keep that on this page. Okay, you might wonder what would happen if he went faster than 12, whoops, erased it. If he went faster than 12 meters per second over the hill. We can do that. Let's just keep it on this page and see what happens. So if we did that, this would be the hill, this would be the guy, this would be mg. And let's put some larger numbers into this problem and see what happens. We'll put a larger velocity in and see what we get. So let's take the v squared over r, or v squared equals gr equation, and we'll use the same radius, but we'll put a larger v into the equation, but this isn't actually the equation we want here. We want to use the full equation that we had at the top of the page earlier. Actually, it's not at the top of the page, it's on the previous page, so let me go over there and grab that equation. So this is a special case equation right here. This only works when you feel exactly weightless. In this case, that would be at down here 12.1 meters per second, but if we went faster than that, what would it feel like? So we have to use the full equation, not just this special case. So I'm going to go grab that equation. So this is the equation that I'm referring to. mg equals m. Okay, this is the actual equation that we want. We want to have the full equation, not just the right side of it. So let's take our guy now and put some new values in. We'll keep his weight as 686, and his mass, of course, would be 70 kilograms. So this would be minus, I'm going to pull this down a bit, so that'd be 70 kilograms. And we'll pick a new velocity, let's say, of 15 meters per second, and that would be squared over the same hill, 15 meters. Now, if we look at the speed that he needed to go to be weightless down here again, we're going faster than that. So what's that going to do? It's going to say that the radial force, let's calculate it first of all. So get your calculator, punch this in. And you get a sort of strange answer of negative 364 newtons. What does that mean? It means that not only does he feel weightless, it's worse than that. The car is going to go out from underneath him. So roller coaster cars are trapped on the track, and the car will take this path. But if the guy is sitting in there and doesn't have a seatbelt on, he's going to go like this in a larger circle because he's going faster, probably to his ultimate demise. Of course, as you know, roller coasters that do things like this, you aren't going to find too many where they don't have some kind of seatbelt or shoulder harness on them. So what the heck does this mean? This is supposed to be F normal, not F radial. I copied it over from the previous page incorrectly. Okay, so what does that mean? It means that as the guy goes over the top of the hill, you not only have his weight helping him go around the turn, but because he's going so fast, you know when you go around the turn quickly, you would have to have a larger force to enable you to do that. So in this situation, we have to add on an additional normal force in the wrong direction, not up, which would be positive as it was before, but down. So the normal force is pushing or pulling, either one, down on this guy, and that allows him to go around the track much more quickly. Now this last one here, you may not completely get that. It's a little bit more sophisticated than the other ones, but give it a shot. Go back, look it over again, and see if it can make sense. It's not something that you have to look at too many times before it starts to make sense. If you have questions on that, put a little question mark here and send me an email, talk to somebody. At worst, we'll talk about it when I get back, but I think you can figure it out before then. Okay, this is probably a good place to stop for today. We've been going about, this video is running about a half hour right now, so you can use the remaining time to, if you have YouTube yourself, you could take a look at it. Of course, you probably need some earphones to do that, or you can work on something else for the last 10 minutes. Remember, the word is work quietly. It doesn't mean you can't talk, but you need to talk quietly so people can hear each other. Oh shoot, I did it again. No, I didn't. I thought I stopped it. Okay, so now it'll officially stop the video. And there you go.